So chapter number 12, physical properties of group 17 elements. We're talking about halogens. Halogen itself, the Latin word means salt-forming species or substances. So since they are used in formation of salts around the world, we call them halogens. They all have 7 electrons in their outer principal quantum shell. The electronic configurations have been given over here. So you'd see the same pattern, S2p5, S2p5 in each and every one of them. We haven't discussed the bottom two. Estrogen is still a mystery for human beings. We don't know much about it. We can only predict what it would look like or how it would behave physically or chemically. And apart from that, there is one more element now below estrogen. It goes actually the same for both of them. So sticking to the first four elements from fluorine to iodine, they're all nonmetals. At room temperature, they exist as diatomic molecules. So it's better to write this one as F2 and this one as Cl2, this one as Br2, this one as I2. And it's better that we understand that if estrogen was to form a formula, it would be 82. Now, single covalent bond is there. These are simple molecular substances, and the state of matter changes from gas. Fluorine is also a gas, so these two are gases, and then this one is a low boiling liquid, and then this one is a solid. So I hope you understand the prediction for 80 would also be a solid. The color is actually going from a lighter or paler color to all the way to darker color over here. So if fluorine is pale yellow, which is not given over here, so we can't really discuss about it right now. So this one is pale green, this one is red brown, this one is gray black. So this one is definitely supposed to be dark black or simply black. So that's how we go with these properties. Anything discussed back in IGCSE is considered as a prerequisite and is considered that you know it already. So not preparing something, being a part of IGCSE, not specifically being a part of A-level book would be stupidity. So keep in mind any prerequisite is something that they assume that you would know and you understand. So the atomic radii increase down the group in this portion. The melting points are also increasing, the boiling points are also increasing, so does the density, and of course the color is getting darker. Now looking at the table for melting boiling points, since they're increasing, the boiling point gives us the idea of volatility, the ease of from which they evaporate. All the values are relatively low because they have simple molecular structures. There are only weak van der Waals forces between their diatomic molecules, and this is because of ID-ID forces. These forces increase with the number of electrons increasing uh, when we go down the group, or because of their increasing atomic number. The greater the number of electrons, the greater the opportunities for instantaneous dipoles arising within molecules, or of course, a stronger van der Waals force between the molecules. So this makes iodine the least volatile and fluorine the most volatile of the halogens. That's why fluorine a gas and iodine are solid at room temperature. This has already been discussed in chapter number 4, the bonding chapter. So I hope you are clear about that already. Now, moving on, reactions. Halogen atom needs to gain one more electron to achieve the stable nearest noble gas configuration. Now, halogens react with metallic elements in the ionic way of reacting. They gain that one electron, they become a negative anions with -1 charge. The example is given for calcium chloride. So when a halogen reacts with a metal atom, it gains electrons. They are actually electron acceptors. So we call them good oxidizing agents. They oxidize other, they reduce themselves, and hence they are known as good oxidizing agents or electron acceptors. So their oxidation number usually is reduced from 0 to -1. For example, for chlorine, it becomes chloride ions in the cyanic compound example. So the halogens also react with many, apart from many metals, many non-metals. Halogen atoms share pair of electrons in those cases. That's actually just an electron sharing would make them stable. So usually we tend to see that halogens make just one covalent bond, and that usually results with a single covalent bond. So we see this thing in non-metallic bonding with non-metals or covalent bonding. But if we go on with repeating the reactions of fluorine with calcium or with hydrogen shown here with other halogens, in these experiments, we'll find that the reactions of fluorine are more vigorous than those of fluorine. Bromine is even less vigorous than that. Iodine is going to be the least reactive of all. So this gives us the idea that halogens get less reactive down the group number 17. Now, before we talk about halogens, I hope you already know that for nonmetals, it is the same trend. Nonmetals tend to get less reactive down the group, whether we're talking about group 4 or 5, or I mean 14 or 15 or 16 or 17. So of course, it's going to be true for group 17 as well. Now, talking about another ability that they show is electronegativity. Electronegativity is actually the ability of a covalently bonded atom. This atom has already bonded covalently, and it actually attracts the shared pair or the bonding pair of electron towards itself. Now, this pattern in reactivity corresponds to the trend in electronegativity down the group. So if we see that fluorine atom has the strongest pull on the pair of electrons, and that is because if I talk about electronegativity as a trend, so this trend increases from left to right in a periodic table, and this also increases from bottom to top in a periodic table, because of which fluorine is considered to be the most electronegative element in the periodic table, right? So this gives us the idea why fluorine has the strongest pull on the pair of electrons in a covalent bond, and iodine has the least pull. Now, electronegativity is usually given in numbers, and that's the Pauling stable. Now, the Pauling stable has the values to a maximum of 4, and fluorine is the only element in the periodic table with that maximum value. This was also discussed back in chapter number 4. Since fluorine atoms is the smallest in the group as per its size, its outer shell is nearer to the attractive force of the nucleus, and the electron entering its outer shell will also experience least shielding from attraction of the positive nuclear charge. So these factors outweigh the fact that fluorine's nuclear charge is only 9 positive compared with iodine's 53 positive. That's why fluorine is much stronger oxidizing agent or acceptor of electron than iodine. So hopefully this gives you the idea of why electronegativity of fluorine is more and iodine is less, or any two halogens for that matter in comparison. Evidence of oxidizing power of halogens, this can be seen in their displacement reactions. Displacement reactions is something that we have looked upon even at the level of IGCSE. We have discussed a simple generic important rule. That's also given over here as an important point. A more reactive halogen can displace a less reactive one from its halide solution. That is pretty much possible for the halogen on the top of the list. Fluorine can actually displace every single halogen in the list. And of course, if we're going to talk about a bottom element such as iodine, of course, it won't have the capability to do the same with bromine or chlorine or fluorine. So let's take an example. When chlorine water is added to a solution of sodium bromide containing bromide ions, bromide negative ions actually, the solution changes to a yellow-brown color. And the color is caused by the presence of dissolved bromine molecules as found in bromine water. So we can safely say that this is because of the displacement. And since chlorine was more reactive than bromine, chlorine displaced bromine and of course, from their bromide ions and converted them into bromine molecules and took its place. This is a very simple displacement reaction, and it's pretty obvious we're talking about non-metal displacement. Well, the rule for displacement is pretty simple and straightforward. Be it metals, be it non-metals, the more reactive one can always displace the less reactive one. So chlorine has displaced bromine from solution. Now, I would really like to notify some very important thing over here, and that is also considered important in A levels from the point of view of examiners. it is also mentioned in the marking scheme. Now notice, chlorine has displaced bromine. We never say that chlorine had displaced bromide ions. No, that's not the right way of saying it. It's a conventional way that we always say chlorine has displaced bromine from its salt solution or bromide or halide solution. So you're not going to say chlorine has displaced bromide ions. This is specifically mentioned. So make sure you don't make that kind of mistake. Now, as this has been clarified for you. So if we talk about the summarized ionic equation, this is chlorine, molecular form, bromide ions. The reaction gives us fluoride ions and bromine, the molecular form. Now, I do understand that you must be thinking, why are we putting aqueous over here and why not liquid? Now, let me tell you that it's pretty common for bromine molecules or iodine molecules or chlorine molecules. Actually, to be honest, they are insoluble in water. If they are supposed to somehow interact with water, they actually tend not to dissolve in it, but to react with it. If I talk about iodine in specific, since iodine is the least reactive, its reaction with water is even slow. So what happens is that it does not tend to dissolve in water. However, it does dissolve in water if there is a halide present. And specifically, if their own halides are present, so if bromide ions are present, the bromine molecules will be soluble in water. So that's why in that case, we may write them as an aqueous solution. I hope this clarifies the point. This also clarifies that why we can write aqueous next to iodine. Since if you go back in chapter number 4, iodine is written as a simple molecular substance. Now, it is clearly mentioned in chapter number 4 that simple molecular substances are insoluble in water. And the first example that they talk about is usually iodine or sulfur. Now, iodine here is written as aqueous. This is because of the presence of iodide ions over here. And that's what we also do in lab. That's actually a paper 3 trick. They're going to tell you, if you take a beaker that has water in it, and if you throw some iodine, iodine is usually present in the form of very small balls or flakes in lab. Usually it's in a form of small balls. It usually isn't present in the form of flakes. So if you throw them in water, actually they're going to settle down. They're not going to get dissolved. So what we do is that we put a little bit of CAIE, potassium iodide, or sodium iodide in water before we throw in iodine. That actually makes iodine soluble. Not just soluble, it gives us the yellow-brown color. Okay, so I hope you understand how it dissolves. If you're looking for an exact reaction of why it dissolves, let me tell you, iodine actually reacts with iodide ions and it forms triiodide ions, which are yellow-brown in color. That's how they are soluble in water. They're actually not soluble in water, to be exact. They are reacting with their own negative ions and forming triiodide ions. But this exactly is something you don't need to know. You simply need to know that this can be aqueous in the presence of this, and the color would be yellow-brown. Okay, so now this clears the part that the simple molecular species such as iodine or bromine are also soluble in water in that case. Coming back to the point, the more reactive halogen can displace the less reactive one in this kind of displacement reaction. So bromine will be able to displace iodine in the similar example, and we will be able to write a similar ionic equation. Now, if I write the exact opposite, if I tend to write it like this, will this be able to do this? So if this kind of stuff comes in front of you, we simply answer it as no reaction. Don't tend to write the product. The forward is possible, the reverse in this case is not possible. The forward is possible, the reverse in this case is not possible. The less reactive one cannot displace the more reactive one. That's how we actually talk about their oxidizing power. And this is actually an evidence of their oxidizing power. So if anyone talks about the oxidizing power or the examiner asks about the evidence, Displacement reactions are actually the evidence of their oxidizing powers. So this is the same thing written over here. Now, oxidizing power is actually the gain of electron or the ability to gain electron, and this decreases group 17. Now, the color of halogen molecules in solution are difficult to identify positively in this displacement experiment. However, the halogens dissolve well in colorless liquids. Cyclohexane, which is immiscible in water, forming two separate layers. So the halogens dissolved in cyclohexane are clearly different colors. Okay, since this was making a little bit of a confusing statement, so that's why they tried to clear it out. Why confusing? Let me take you right back. Okay, so we were talking about this one, and we mentioned this as yellow-brown appearance. And when I was talking about this one as well, I also mentioned this one as yellow-brown appearance. Now, these two give you the same color. How would you understand what kind of displacement reaction was it if by the end of the reaction, both of them give you the same color? So that's why the book author is talking about this. Now, I would appreciate for your understanding, you might write colorless organic liquid. This actually clarifies the whole sentence a lot more because we then come to understand the cyclohexane is organic. This also gives you the idea that as soon as we use the word organic liquids, we're talking about solvents that are non-aqueous, which means we're not aren't talking about water anymore. Okay, so you can add some of the organic solvent after mixing the halogen or halide solution, taking the mixture, then allow the reaction mixture to settle. If there is a liquid, organic liquid, and if there is water present, it will clearly show which halogen is present as its diatomic molecule. And that's how it gives you the idea. The pale green, the red brown, and the purple color gives you the idea. So cyclohexane forms a layer on top of water, clearly telling you that water has more density and cyclohexane has less density. Dissolved chlorine is very pale green color, upper organic layer, of course. Bromine is orange, iodine is purple. These colors give you a very good idea what they should look like. And since in aqueous medium they were giving the same colors, it's actually a little bit harder to identify them in aqueous medium. That's why we used an organic or non-aqueous medium. Now, reactions of halogens with hydrogen. Halogens form hydrogen halides when combined with hydrogen gas. Now, this part is important, and I hope you understand that when we are forming hydrogen halides, they aren't exactly acids then. So you should be able to keep the difference between both. Now here, let me go with a couple of examples before I compare the status symbol and the difference between the acid and the before acid parts. So one example of this reaction of hydrogen with chlorine, it gives you hydrogen chloride gas. Same happens with fluorine, hydrogen fluoride, hydrogen bromide, or hydrogen iodide. The description of reactions is given over here, which gives you the idea that the reactivity is maximum with fluorine and minimum with iodine. But the point I'm trying to make before I get to the reactivity comparison portion is that HCl gas means hydrogen chloride. HCl aqueous, when this gas is dissolved in water, is known as hydrochloric acid. So you should be able to differentiate between both. Now, this might be the acid, but at this point, it's just a gas. Okay, so if you look at it, reacts explosively even at cool, dark conditions. For fluorine, reacts explosively in sunlight, slowly in indirect light, what we can say. For bromine, it reacts slowly and it requires actually heating. Consistent heating would better. And iodine's reaction is slow and reversible. That's the only equation in which you'll see the reversible reaction sign, and it requires heating. and it still forms an equilibrium mixture, which means the reaction never goes to completion. Now, the hydrogen halides formed differ in their thermal stability. Of course, we can thermally decompose them if they are weaker in their formation or if they form slowly. If they form fast in a vigorous way, their thermal stability would be much better compared to the former one. So hydrogen iodide, as I've said earlier, can be decomposed by inserting a red hot wire in a sample of hydrogen iodide gas. Purple fumes are seen for iodine vapors. By contrast, hydrogen fluoride and hydrogen chloride are not decomposed in temperatures up to 1500 degrees centigrade. This clearly describes the thermal stability I just given you a description for. So hydrogen bromide is not as well stable as HFNHCl, but it is more resistant to decomposition than hydrogen iodide. At 430 degrees centigrade in a closed container, 10% of an HPR sample will decompose, and around 20% of HI decomposes at that temperature. So thermally stable, HF is most thermally stable, HI is least thermally stable. That's a very good way of showing it. Now, this trend and this trend can conform one another, since the Born energy should be higher for something that is more thermally stable, and the Born energy should be lower for something that is less thermally stable. So of course, the Born energy for HF is supposed to be the highest as compared to HI. Now, Born energies decrease down the group 17, making it easier to break the hydrogen-halogen bond. This is mainly because of the halogen's atomic size. Iodine is the largest atom. Overlap of its outer shell with hydrogen atom gives you a much larger bond length than as compared to the smaller halogen atoms. So of course, these two are indirectly proportional. So we do understand that if the bond energy is lower, the bond length is longer. If the bond energy is higher, the bond length tends to be smaller. So the same thing is given over here, and then it is connected to their thermal stability. So moving on, reaction of the halide ions. Now, in order to talk about the reaction of halide ions, I hope you remember that we have tested them with silver nitrate. Now, the experiments for silver nitrate back in IGCSE were very easy. We used to just form the precipitates and differentiate them on along with their precipitate colors. Chloride, bromide, and iodide ions were used by simple chemical tests. We acidified them with dilute nitric acid. We then added silver nitrate, precipitate forms. If the precipitate was white, it was silver chloride, green, silver bromide, yellow, silver iodide. These were very easy. Now, these precipitates are also a little bit similar in their colors when you're actually going to perform that. So what we do is that you can use a further test to help distinguish one precipitate from the other. We can add ammonia solution, dilute ammonia solution followed by concentrated ammonia solution to verify the result. Now the results are shown as that the silver nitrate tends to react with the halide ion. It forms the silver halide and it gives you the nitrate ions. The silver halide is represented by AgX and the halide ions are represented by X negative. Simply speaking, the nitrate ions are the spectator ions and they don't get involved in the reaction. Silver and halide ions are actually what we are after. So of course, that would be the ionic equation for the reaction. Now, ammonia can form complex ions that are soluble in water. What are complex ions? That's another kind of bonding, which we have kept for A2. So let's keep it for A2. Just keep in mind, it is something more important or something that has been on top of what we have already studied for bonding. So silver chloride, as it forms a soluble complex with dilute ammonia. Silver bromide, as it forms soluble complex with concentrated ammonia. Silver iodide precipitate does not dissolve in adding dilute or concentrated ammonia solutions. So that's how it becomes easier for us to explain them. Because dilute ammonia is going to dissolve those precipitates. Concentrated ammonia is going to dissolve bromide precipitates. Dilute will dissolve chloride precipitates. Concentrated will dissolve bromide precipitates. and both won't be able to dissolve silver iodide. So white, off-white, yellow, and they are really pretty close to one another. If you're going to perform this experiment with your own hands in lab, yeah, the yellow would be really easy to distinguish, but white and off-white, they're really difficult. So what we do is that we then, on top of the precipitate colors that we get, we have two more steps to go with: addition of dilute ammonia, addition of concentrated ammonia solution. So chloride is going to dissolve in both. Bromide is only going to dissolve in concentrated, and iodide is not going to dissolve in either. That's a very good way of checking them. This is important for paper 3 specifically. Now, the reactions of halide ions with concentrated sulfuric acid. Compounds that contain chlorides, bromides, or iodides would react with concentrated sulfuric acid. All of these reactions produce one or more toxic gases, so they must be performed with great care, either in a fume cupboard or a very well-ventilated space in which you tend to stay away from the gases. It's better that if it's a teacher's demonstration and students are not allowed to do it on their own, if they're allowed to, it should be done with extreme precaution. So we can prepare hydrogen chloride gas by dropping concentrated sulfuric acid slowly, remember the point. If you're going to do it on your own, please be careful. So onto the crystals of sodium chloride. So what happens? Concentrated sulfuric acid and concentrated sodium chloride and concentrated sulfuric acid goes in there. We have a big long special funnel for the purpose of our safety. So of course you can see the whole thing. Then there is a gas jar, and we can collect hydrogen chloride on the other side. So this is what the reaction is going with. It produces NaHSO4 and hydrogen chloride. And the hydrogen chloride produced is visible as white fumes. So we cannot use the same reaction to prepare samples of pure hydrogen bromide or hydrogen iodide. So section 12.2, how it gets increasingly easy to decompose hydrogen halide going down the group. So this gives you the idea that even if we are going to prepare them, it's actually easier to decompose them. And since this reaction is exothermic itself, so they might get decomposed automatically. That's why this sentence is written over here. So when the hydrogen halides decompose into their elements, the halide part of the molecule in HBr and HI is oxidized. Concentrated sulfuric acid is relatively a good oxidizing agent itself. It is not strong enough to oxidize HCl, but concentrated sulfuric acid will oxidize and decompose HBr and HI. So any HBr or HI formed in the reaction between sodium bromide and sodium iodide and concentrated sulfuric acid undergoes further oxidation. So there you see, this is going to be the actual initial reaction, but since HBr can be oxidized by H2S4, so it's going to follow this reaction, and this is the products that you're going to get. Now, as soon as you look at it, you understand why we were talking about toxic or poisonous gases. So a reddish brown gas is seen, of course, the bromine gas. Since this is elemental bromine, but being exothermic, it would easily be converted into gaseous form. With sodium iodide, the sulfuric acid is reduced to several sulfur products as it oxidizes. So the hydrogen iodides formed to different extents. The products of oxidation of HI are, let's take a look at it, and you're going to see many different reactions over here. So this is the initial reaction forming HI, but of course, HI can be oxidized by sulfuric acid. So let's take a look at it. The first reaction, iodine plus SO2, the second reaction, iodine plus S, the third reaction, iodine plus H2S. So you can actually make several observations. The more sulfuric acid you're going to use, the different products you're going to form. So the first reaction gives you the iodine and SO2. The second reaction is going to form sulfur. Sulfur here would be a yellow solid. H2S has a very strong smell of bad spoiled eggs. Now, this is one of the gases that can induce a lot of vomiting in the lab. So we tend to keep this gas as less as possible for sniffing or other purposes in lab, even during performing of experiments, because what I'm say is pretty true to its extent. I've seen that with my own two eyes. So yeah, many of the students are unable to control themselves when they get a good sniff of H2S, but this is not a good gas for your health. So of course, and the smell of bad eggs itself is easily capable of inducing vomit. So iodine is produced as a violet purple color. So you can see in all the reactions, iodine is the common product. Now, therefore, NABR and NI produce a mixture of gases when they react with concentrated sulfuric acid. So this is not a good way to prepare a sample of gases for HBr or HI. The point we were trying to make is that it's easier to oxidize the hydrogen light through going down group 17. In the reaction above, the bromide ions in HBr or the iodide ions in HI act as reducing agents. The bromide and iodide ions are electron donors. They reduce the sulfuric acid. They themselves get oxidized. Their number increase from -1 to 0. And hence, we can say that they are converted into Br2 or I2. So bromide and iodide ions are oxidized. The halide ions are increasingly effective as reducing agents going down group 17, which gives you an idea that how they behave. Now, disproportionation reactions. We have studied disproportionation reactions in a chapter before. That was probably chapter number 7, the oxidation reduction chapter. But their disproportionation reaction was just an oxidation reduction point that we were discussing. Here we are going to consider the same disproportionation, self-oxidation reduction reaction in a similar way, but this time we're going to go for a deeper understanding. We're going to talk about the reactants, we're going to talk about their conditions or the temperature, and discuss what would happen and which products can actually form depending upon the different conditions, on top of everything, specifically temperature. So chlorine in cold alkali at 15 degrees centigrade, you can see apart from water and NaCl, this is NaClO forming. Here, chlorine is showing us two different states, +1 and -1. So in reduction reaction, chlorine is getting reduced, Cl2 is being converted into Cl negative, but in the oxidation reaction, chlorine is being converted from Cl2 to ClO negative, in which Cl state is +1. However, for a different set of conditions, chlorine in hot alkali, 70 degrees centigrade, now hot concentrated aqueous sodium hydroxide solution can produce something different. Instead of NaClO, you can see NaClO3 forming. Now this time chlorine is getting disproportionated in two ways, from 0 to -1 and 0 to +5. So you get an idea what can form. This is a more appropriate explanation to the previous disproportionation reaction. Chlorination of water, last point, something we have studied back in IGCSE as a part of safety technique, also as a part of water purification. So adding a small amount of chlorine to a water supply, a huge amount of water, of course, will kill bacteria and make the water safer to drink. So this is what happens in a reaction. Let me remind you, this reaction was present back in IGCSE chapter number 3. So I hope you understand the reaction already. So we do understand the chlorine is going from 0 to -1 and +1 states. It is producing HClO. HClO is known as chloric 1 acid. It actually sterilizes water by killing bacteria with its atomic oxygen, the oxygen atom with it. And this also acts as a bleaching agent. Now, some of the ClO dissociates in water to produce ClO negative ions. It acts as a sterilizing agent. The same ClO negative ion can also act as a bleaching agent, and they can turn colorful substances into colorless substances. And I guess that's about it.